Hi everyone, I am Nils Paulsson, and I'm going to talk about XTU, a simplistic approach for turning your beautiful models into running code. I do this presentation as the founder of Lonefield CND, which is the sole sponsor of the XTU project. In my other job, I develop AI-supported autonomous airborne systems.
In short, XTU is used for turning your platform-independent model, or PIM, into a platform-specific model, or PSM, using handwritten code. Now, why would anyone handcode a PSM when we have model compilers? My wife would probably say it's because I want things my own way. My story is a bit different. About 10 years ago, I was working on an AI project targeting a smartphone platform. The app was our soft real-time system that should sample a significant number of sensors, process the acquired data, and drive the HMI with low latency. In essence, I needed all cores provided by the hardware. I had the drawings of my executable UML models, but no suitable model compiler. Also, I was lacking the resources to write a model compiler from scratch. So I took a different approach. I started with a list of the formal platform-independent building blocks: domains, signals, classes, states, and so on. Then, I implemented each building block using native Java templates. When that was done, I could simply use these templates to handcode my platform-specific model, compile it, deploy it, and finally run it on my Android phone. However, it was very clear from the beginning that implementing object relations using Java templates would be a major undertaking. Instead, I decided to translate relations by brainpower and implement them using Java containers, references, and so on. Taking a few steps back, I essentially developed a partial model compiler that used Java templates for PIM notation, as opposed to, for example, UML. It worked quite well. In fact, it worked so well that I took the same idea to my other job. There it has been used for research and development in the area of autonomous aircrafts. The largest model included about 20 domains and 100 classes. The most interesting benefit was the deployment flexibility. The same model could with little effort be deployed on single-core, multi-core, and distributed mixed platforms. We even deployed the models on a multi-million-dollar flight simulator. This brings us to XTU. XTU is the generic C++ open source version of the initial Java Android implementation. In other words, XTU is a partial model compiler that uses C++ templates as model notation. Let's take a look at the architecture, and we will do this from a side view perspective. At the top we have the blue PIM, and at the bottom we have the red PSM. In the PIM we have C++ building blocks for classes, finite state machines, states, events, and procedures. Relations do so far only belong to the PSM, but that may change in the future. Furthermore, we have PIM components for domains, asynchronous signals, and synchronous operations. Bridges are partly PIM and partly PSM. The different PSM parts are used for different deployment scenarios. The platform-specific models also include an execution context for managing threads and a scheduler for scheduling signals, operations, and events within a given execution context. Let's get a bit closer to the code and see how the building blocks map to C++. Domains map directly to a template called domain T. Bridges map to a base template, bridge T, which is the PIM side of a bridge. The PIM bridge is inherited by a particular PSM bridge, depending on if a bridge shall be single or multi-threaded. Future versions of XTU will also support distributed PSM bridges. Signals and operations are mapped to corresponding templates, and classes with a non-trivial lifecycle are implemented by the class T template. Trivial classes, that is, classes having a simple construction-destruction lifecycle, are implemented using ordinary C++ classes. State machines are included in the class T template, but their state table and transition rules have templates of their own. So do states and events. Finally, procedures are implemented using ordinary C++ functions or methods. There are a few reasons for using C++ templates. The first is to provide type safety at compile time, so that, for example, only valid signals are handled by a particular bridge. This is an important aid when hand-coding models. The second reason for templates is to generate static classes at compile time. These can be referred to by their type name alone, thus eliminating the need for an extra layer of object instantiations. The third reason is that templates provide virtual static methods that are resolved at compile time. An executable UML model has a surprisingly large amount of constant data. This brings us to the fourth reason. Templates allow evaluation of constant expressions at compile time, not at runtime. Let's focus a bit more on bridges. The PIM part of a bridge has a requiring side and a providing side. Signals and operations can only flow from the requiring side of the bridge to the providing side. This makes the bridge directional, and this is very useful in security and safety-related systems, where solid separation is vital. The type of a bridge is unique for each requiring providing pair. Domain A can thus only send signals to domain B using the AB bridge and vice versa. This is a key design element, allowing type-safe domain connections at compile time. Let's switch to the PSM part of a bridge. XTU currently supports two kinds, single and multi-threaded bridges. A single-threaded bridge connects domains that operates within the same execution context. A multi-threaded bridge connects domains from different execution contexts. This is done by a single producer, single consumer FIFO buffer. And with this approach, bridges introduce a flexible concurrency scheme in the PSM. A fundamental aspect of this bridge design is that a domain can be deployed in one and only one execution context. Thus, an application may have at the most the same number of execution contexts as there are domains. XTU has a default generic scheduler that prioritizes performance over predictable timing. The scheduler handles posted and delayed events, as well as signals and operations received over multi-threaded bridges. Signals and operations over single-threaded bridges are issued immediately at the very place in the code from which they are sent. Self-directed events are processed immediately after the current state procedure has finished, and this is managed by the state machine outside of the scheduler. Let's put some numbers to XTU. Current version, which is version 2.0, targets C++ 11, GCC version 7 or higher, and it depends only on the STL, the standard template library. That is all, so it's fair to say that XTU has a decent platform independence by itself. These four benchmarks were compiled and run on Linux using four different hardware platforms: Intel i7, AMD Threadripper, Raspberry Pi 4, and Raspberry Pi 2. The tests were compiled for small code size. However, XTU responds well to speed optimizations, so it's possible to get even better performance, in some cases up to 50% improvements. The 4 tests are self-directed events, events posted to other class instances, sending signals over multi-threaded bridges, and finally calling operations over a multi-threaded bridge. As we can see from the first test, self-directed events are processed at a very high rate, and posted events are doing fairly well. The tests for multi-threaded bridges are heavily influenced by latency induced by the operating system's thread scheduler. Test number 3, the signal test, is essentially hammering the bridge. As soon as the receiver buffer is full, the requiring thread has to wait for the provider thread to empty the bridge buffer. Test 4, the synchronous operation, is of course even more influenced by latency from the operating system. What are the real benefits of the XTU approach then? Well, you can go from model to running code with limited effort. There's a strong association between the PIM and the XTU framework, which makes it easy for a code-centric developer to see how a graphical model is mapped to C++ code. Integration with existing C++ API is of course also straightforward. XTU supports a wide variety of deployment scenarios, relying on its straightforward concurrency model. The scheduler is modular, and the same application can have different schedulers in different execution contexts. One context can have a real-time scheduler, and another context can have a scheduler more suited for raw performance. Since the abstraction level of XTU is similar to the platform-independent model, XTU is also well suited to be the backend in a code generation solution. XTU is probably best suited for smaller development teams that have a working, constructive communication going. The main reason being that the model on paper and the running code are kept in sync manually. Finally, a somewhat unexpected outcome is that you can get a long way by using domains and bridges only. That is, writing the internals of a domain in a more traditional object-oriented manner. What are the potential drawbacks then? Well, I would like to say none, but the most obvious is that you need knowledge of C++. The largest obstacle is when you have to do large structural changes to a model that has already been implemented using XTU. That may require significant revision of the code, which can be mentally challenging. The start and shutdown code may also be a bit complex when trying to gracefully boot or shut down multiple domains and execution context in an orchestrated fashion. We're approaching the end of the presentation, so let's spend a few words on possible future development. We have already talked about distributed bridges. Support for Data and Darwin's type system would be a really useful addition, as would better FSM debug support. Current default execution context only yields to the operating system when there is no more work to do. A more energy-conserving approach would be to put a context to sleep. A code generator would be nice. The current idea in this regard is to hook up with Leon Starr's work on Scroll. Finally, the ultimate goal is a relational model using C++ templates. The XTU project is hosted by SourceForge, and I would like to invite you all to use XTU, to improve XTU, and to contribute to XTU. And there we are. I end this presentation with a code snippet of a bridge definition from the XTU wiki. There you can find a fully functional application example together with documentation of how it works. And with that, I want to say thank you for your time and attention.